Okay, we're going to be talking about part 3, non-truthful sample complexity. Again, thanks a lot for Yideng Fang and Yingkai Li for answering your Q&A in the chat. Okay, again, to review the context, mechanism design looks to identify mechanisms that have good equilibrium. The revelation principle says that if there exists mechanisms of good equilibrium, there exists mechanisms of good truth-telling equilibrium. The proof is quite simple. It's based on the truthful mechanism simulating the agent strategies and the non-truthful mechanism. Because of this, literature focuses primarily on truthful mechanisms. There are 3 issues that I want to address about this focus on truthful mechanisms, and they are, well, most mechanisms in practice are not truthful. Moreover, truthfulness is not without loss for the kinds of mechanisms we like to design in computer science, like simple or prior independent mechanisms, and it's not trivial to undo the revelation principle. For our goal today of sample complexity, these issues are especially crisp. For instance, sample complexity in the literature tends to assume that the designer has access to samples from the value distribution, which is the true preferences, and then can design a truthful mechanism for agents with values from these distributions. If we want to move to non-truthful mechanisms, we have 2 challenges here. One challenge here is that, well, the values that we might have had from past mechanisms are no longer truthful values. Those bids in past mechanisms are in fact bids in equilibrium, and we have a challenge of getting values from bids. And moreover, we now need to design a non-truthful mechanism from these, values or bids. And doing so with imprecise distributional knowledge is an additional challenge. Cool. So, our goal here is a theory of non-truthful mechanisms, one that is compatible with the kinds of questions we've are liking to ask. And in particular, for this session, we'll be talking about sample complexity. Cool. So let's just remind ourselves about the bad welfare equilibrium in winner pays bid mechanisms. Okay, so winner pays bid, highest bid wins mechanisms can have very bad equilibrium. Let me give you a quick example coming from single-minded combinatorial auctions. So this is an example we talked about previously, but let me just go over it again just to make sure we're on the same page. So I'll have M items for sale, and we'll have M plus 2 agents. We'll have little agents indexed by I, where each of those little agents, I, desires the item, just the item I, and has value vi equal to 1 for that item. And these two agents H, which will be big agents, they desire the full grand bundle of items. They want every single item, but their value is only 1 for every single item. Good. So here is a Nash equilibrium. The big agents both bid 1. One of them wins, one loses. The little agents all bid 0 and all lose. Notice that here all agents have utility 0 because they all had values 1. So one of them won, but they paid 1, so their utility is 0. Everyone else loses, so their utility is 0. And notice more that for any bid less than 1, anyone deviating to a bid that's less than or equal to 1 is going to have 0 utility. And of course, deviating to a bid over 1 has negative utilities. So this is an equilibrium. I want to point out, though, this equilibrium has really bad welfare. In fact, the welfare is 1. Only one of the big agents wins. But of course, the optimal welfare would be to allocate each little agent I, the item they want, and get a value of 1 from that, which would be a total welfare of 1. Okay, so the Nash welfare is very far from the optimal welfare. Okay, so the goal for this part 3, is to get welfare that's basically opt minus epsilon. So we want to get arbitrarily close to the optimal welfare. And so we're a long way from getting there with this mechanism. Cool. So we're going to be looking at sample complexity and mechanism design. The story of sample complexity and mechanism design is let's use past bid data to improve a mechanism. And the online marketplaces have lots and lots of past bid data, and so they could potentially use this data to improve the mechanism and get mechanisms that function better using this data. Okay, so here's the definition of truthful sample complexity. There are a number of samples and epsilon coming from a value distribution. And the question is, how many samples are sufficient to identify a truthful mechanism that has expected performance within an additive epsilon of the optimal performance? Okay, usually people ask this question about revenue, but you could also ask this question about welfare, and it's a non-trivial question for non-truthful mechanisms. Okay, here's a observation. If the designer in fact ran a truthful mechanism, then the designer can re-optimize this truthful mechanism from truthful data, and everything is sort of consistent. The past mechanisms were truthful, so you have truthful bids, and you have these. You can use these bids as samples and design from them a mechanism that's also truthful, and things are sort of consistent. Great. But of course, there's this practical issue we discussed before, which most mechanisms in real life are not truthful. And so past bid data is not truthful. And we're going to need to design a non-truthful auction with this past bid data. So this has a lot of challenges. The first challenge is that if we were to say try to infer values from bids, this might require strong assumptions on the value distribution of the mechanism to be able to do this well. And the second challenge is that it's non-trivial to design Bayes-Nash equilibria in non-truthful mechanisms. Cool. So part 3 of this tutorial is on non-truthful sample complexity. The plan is to overview counterfactual inference, and then talk about inference in IID position auctions, which are symmetric environments, and then give a reduction from IID position auctions, a general reduction from general asymmetric auction problems to IID position auctions. This section is going to give a brief introduction to counterfactual inference in auctions. The following will be a running example that we're going to use in the section. So we're going to look at a 3-agent environment, and we'll look at a mechanism that's highest bid wins and winner pays bid in 3 scenarios. The first scenario, auction A, is when there's 1 unit for sale. So this highest bid wins, winner pays bid mechanism is equivalent to the single item first price auction. Auction B is going to be the case there are 2 units for sale. Okay, and so highest bid wins, winner pays bid means we ask for bids, we sort the bids, the top 2 bidding agents win. Each of those agents pays their bid. The lowest bidding agent loses. And auction C is going to be a mix between these 2 auctions. This is going to look like a winner pays bid position auction, where the agent with the highest bid gets the first position and is allocated with probability 1. Agent with the second highest bid gets the second position, is allocated with probability 1/2, and the agent with the lowest bid is allocated with probability 0. Great. The question we're going to be asking is, suppose we have equilibrium bid data for auction C. How can we estimate the revenues of auction A and auction B? And so, why might this situation have arisen? Well, maybe we were trying to do a randomized experiment between auction A and B, but perhaps we didn't tell the bidders this, and so we randomized between auctions A and B, but the the bidders just bid as if they didn't know which auction was being run, so they bid in auction C, which is the convex combination of the two auctions. And now we have the problem of estimating the revenue auction A and B from equilibrium bids in auction C rather than equilibrium bids in auction A and B. Great. So the following assumption is going to be sort of the main guiding assumption that's going to allow us to do counterfactual inference. So the assumption is that bids are in equilibrium, and in particular, they're in best response to the competing distribution of bids. The main econometric observation we're going to be using is that this competing distribution of bids is actually exactly what we observe in the bid data. Okay, so imagine that we're trying to infer what bidder one's value is. And so we could look at the empirical distribution of bids from bidder 2 and bidder 3. So here what we've done is we've taken a lot of samples of bidder 2's bid distribution and bidder 3's bid distribution. We've taken those bids, we've plotted them in decreasing order. And so then we've shown them sort of the Quantile function for this empirical bid distribution. Okay, good. And this looks like basically a sampled version of the uniform distribution on 0, 1. Great. Given the empirical bid distribution, we can ask what is the empirical allocation rule that bidder 1 is facing. In other words, given that we're running auction C, which is this position auction with position weights 1, 1/2, and 0, what is the allocation probability that bidder 1 gets for any bid they could put in? And we can get this basically by simulating, for example, with the bids that we have in our empirical bid distribution, and then plotting the result of the simulation. Okay, and so here it looks basically like a linear function with slope 1 up to 0.1, and of course all the bids are less than 1, and so when agent 1 bids strictly more than 1, agent 1 is going to win with certainty. Great. So having identified the bid allocation rule, we now can say, okay, here's our approach. Given the bid distribution, we're going to identify this bid allocation rule, and then we're going to solve for what a bidder strategy is. So given the bid allocation rule, imagine any value the agent might have. Let's figure out what is the best bid for the agent with that value. Okay. So given the bid strategy, then, we can invert this bid strategy to map the agent's bid back to what their value should have been. Cool. Let's run through this with our example. Okay, so our question is, how should agent 1 bid in auction C? Good, so we're going to ask, what is the expected utility of agent 1 with value V in bid B? As usual, that's given by this formula for a winner pays bid mechanism. It's value minus bid times the probability that agent 1 wins with bid B. We just saw that is given by this formula, bid allocation rule, and we saw that. Well, look, so again, understanding this utility, the utility the player gets is the width of a rectangle with width V minus B times the height given by the allocation probability at bid B. Okay, so the agent's trying to optimize the area of that rectangle. Awesome. We're going to approximate this empirical bid allocation rule by smoothing it, and when we smooth it, we see, oh, it's just a 45-degree line, x equals y. Okay, so the probability that agent 1 bids with bid B is just B. Now we have a formula, and we can do calculus. We can take the derivative with respect to B, set it equal to 0, and solve, and determine that it's optimal for agent 1 to bid half of her value. Great. Well, if it's optimal for agent 1 to bid half of her value, then we confer that an agent with bid B has value equal to 2B. Great. So our bids, recall, were uniform on 0, 1. And so from this, we can infer that the values are uniform on 0, 2. Great. With values that are uniform on 0, 2, we're now in a good position to calculate the revenue of any of our auctions that we were considering, auction A, auction B, and auction C. So let's remember to calculate revenue. First, value order statistics evenly divide the interval they're over. And so we have 3 bidders. And so they're going to evenly divide the 0-2 interval. And in particular, the expected highest value is going to be 3/2. The expected median value is going to be 1. And the expected lower value is going to be 1/2. All right, now we can calculate the revenue of auction A. Remember, auction A was a single item, 3-bidder auction. Okay, so given this bid distribution, we're going to use revenue equivalence. This is a first price auction. It's revenue equivalent to the second price auction. And the revenue of the second price auction is the expected value of the second highest bidder. Okay, and that revenue, the expected value is 1. Great. Auction B was a 2-unit 3-bidder auction. Great. This 2-unit 3-bidder auction is revenue equivalent to the 2-unit third price auction. The 2-unit third price auction has revenue equal to twice the third highest bid. So that revenue is exactly equal to 2 times the expected value of the third highest bid, which is 1/2. So it's going to have a revenue of 1. Finally, the revenue of auction C. Well, auction C is just a convex combination of auctions A and B. And so its revenue is a convex combination of auction A and B's revenue, which is going to just be 1. So we see for this particular bid distribution, or value distribution, sorry, the value is uniform 0-2. The revenue of all of these auctions is just 1. Of course, if we had a different value distribution, we could have observed that the revenue of auction A was bigger than the revenue of auction B, or vice versa. Great. That concludes our brief introduction to counterfactual inference. Okay, in this section, we're going to talk about inference in IID position auctions. As references, one of the original papers on inference in auctions is Guerre et al. But most of the results I'm going to be talking about are in this paper with co-authors Shuti Chawla and Denis Nikopelov called Mechanism Redesign. Great. So we're going to be talking about doing inference for IID position auctions. So again, recall that an IID position auction is given by M positions with weights W1 in decreasing order to Wm. Imagine I have M agents with values IID drawn from some distribution F. Okay, the agents submit bids. They're going to be assigned to positions in decreasing order of bid. So agent who's going to be the jth highest bid is going to get allocation probability Wj. And all the winners, the ones that are the win if their allocation probability realizes to 1, are going to pay their bid. So the goal of this part of the tutorial is to come up with an estimator that from bids in equilibrium in position auction C, we'll be able to estimate the revenue of position auction B. Okay, first we're going to have a little review of how to think about revenue in auctions in general. And so the distribution F is going to be defining how the values are drawn. It'll be convenient to actually represent that in terms of the demand curve. Okay, so the distribution function F can be converted into a demand curve by taking its inverse at 1 minus Q. And so this is imagining an agent with a quantile Q drawn uniformly from 0, 1, where low quantile agents are strong, high quantile agents are weak. And this, for the uniform distribution, gives this inverse demand curve. Okay, so here we're plotting agents from this distribution with quantile between 0 and 1. And the lowest quantile agent has value 1, and it's decreasing linearly to the highest quantile agent having value 0. Great. The revenue curve is going to plot as a function of posting a price that has sale probability Q hat. Okay, the revenue we get from posting the price that corresponds to that sale probability. Okay, and posting a price with sale probability Q hat is coming back to the inverse demand curve, post the price equal to V of Q hat. Okay, and if we post a price V of Q hat,
this has sale probability Q hat, so a Q hat measure of these buyers will buy, and so the expected revenue from posting that price is R of Q hat equal to Q hat V of Q hat. Okay, so this is the revenue from posting a price that has sale probability Q hat. Okay, so we can plot this for the uniform distribution, and we'll get this this function. Okay, and geometrically, and this is going to be useful later in the tutorial, geometrically, we can interpret prices here as lines from the origin that cross the revenue curve. Okay, so in fact, this red line is the line with slope V of Q hat, and thus we evaluate the revenue curve at Q hat, we get the revenue V of Q hat times Q hat. Okay, we can depict this revenue back on the value curve as the area of this rectangle. Okay, again, with width Q hat and height V of Q hat. Great. It's going to be useful to consider allocation rules, interim allocation rules, in quantile space rather than value space. And so we can map an interim allocation rule x of v into quantile space by saying y of q, the interim allocation rule in quantile space, is going to be equal to x of v of q. Okay, and then there's the following theorem will give us a formula for revenue of an auction with allocation rule y and an agent with a revenue curve r. That revenue is just the negative integral of the revenue curve times the derivative of the allocation rule. Okay, and why is this the case? Well, we can view the allocation rule y as drawing a random quantile, Q hat, from the distribution with density minus y prime. In other words, the allocation rule is going to be a decreasing function of quantile, and one way to implement this allocation rule is to draw a critical quantile Q hat from the distribution with density minus y prime, and offer V of that quantile. So offer post a price V of Q hat. Okay, this mechanism has allocation rule exactly equal to the allocation rule of y. And then by revenue equivalence, the revenue of any auction with the allocation rule corresponding to y has the revenue of this randomized posted pricing. But by the definition of expectation, if we're drawing a critical quantile Q hat and posting the price that corresponds to that quantile with density minus y hat, then we can use the definition of expectation to write our expected revenue this way. Okay, it's the revenue we get from posting that price times the density function of the posted price. Okay, and again, this minus sign is in front here. It comes from the fact that y is a decreasing function, and so the density, the derivative of y is a negative, it's negative, and so the density is actually the negative derivative. Cool. So that was how to calculate revenue. I now want to revisit this idea of inference in auctions, and I want to give a formula for how to calculate the value of a bidder from the bids we observe in the auction and the allocation rule of the auction. And I'm not going to go into the details of this formula. It's fairly easy to derive. What I just want to point out is, look, you've got a derivative here. You got something with the allocation rule, and you got the derivative here. Where does this all come from? This comes from that inversion step. This comes from looking at the bidder's first order condition given the empirical bid distribution. Okay, so if you were to write out the agent's utility, you could differentiate it and set it equal to 0 and solve for what how an agent should be bidding, and then you can invert that to figure out, well, what is the value that an agent must have given how they bid, and you would exactly get this formula. Great. So unpacking this formula, we know the allocation rule and its derivative for the mechanism we ran. Okay, so we ran auction C. We know the allocation rule of auction C. In this formula, and denoted here in blue, are the estimated bid function and its derivative, which I called b hat and b hat prime. These are the bid function for auction C, which have to be estimated. Okay, from auction theory from the previous slide, we have an equation for revenue in auction B given the value function, and we can get basically an estimated revenue by plugging in our estimate of the value function that we got from the inference equation. Okay, and so again, this estimated value function is something we have to infer from the data, but the allocation rule of auction B is something we know. Okay, and here I've just plugged in the formula for the revenue curve. Remember, the revenue curve is Q times V of Q. Okay, so I can infer values using my inference equation. I can calculate revenue using my expected revenue equation, and I can combine them. So a little bit of discussion of this approach from classical inference. If you were to do this in the most straightforward way, you take n samples from the capital N samples from the bid distribution. You can estimate the empirical distribution with a rate of square root n using a bit coming from the law of large numbers. To estimate the derivative, you'll need to do some kind of smoothing like we did previously. And typical estimators for the derivative are going to have a worse rate than the square root n rate that you get from the law of large numbers. And thus, the revenue estimator you get in this way is going to have a worse rate than the square root n optimal rate. Cool. What I want to do now is talk about a direct approach for estimating values, estimating revenue of an auction B directly from bids that are in equilibrium in some other auction C. And the idea is basically straightforward. We're going to take this bid allocation rule and we're going to plug it into the revenue equation, and then we're going to simplify. Okay, so we first combine them and we get this formula. And the thing that we don't like about this formula is the lower rate of the sort of the difficulty it is to estimate the empirical derivative of the bids. Okay, so we don't like this term b hat prime. But revenue is an expectation, meaning there's an integral of this whole term. And everything not in blue is a term that's known exactly from the definition of the auction rules. Therefore, we can factor this into coefficients of the bids and coefficients of the derivative of the bids. And then we can do integration by parts to swap where the derivative is. Okay, so integration by parts is a tool that lets us take this b hat prime times some coefficients that are based on the allocation rules, and switch where the derivative is. So we'll get some different coefficients and just the empirical distribution of bids, not the derivative of the empirical distribution of bids. Okay, so simplifying with integration by parts, we'll end up with a formula that looks like some function times the empirical bid distribution. Great. So we'll need to do some analysis to bound this error. And essentially what we need to do is bound this term here, which is the error in the true expected value from the empirical estimator using the integral, which is these coefficients we get times the difference between the true expected, the true bid function and the empirical bid function. Okay, and the estimator we're going to get here is again is going to be replacing this integral with the discrete sum over the capital N bids you get. So it's going to be just a weighted order statistic. Okay, what do? We take our N bids, we sort them, and we sum the sorted bids multiplying by coefficients that we get from discretizing this function W. This estimator is going to have error rate, the optimal rate of root n. Great, so that's our overview of inference in IID position auctions. Okay, this section is going to look at non-truthful sample complexity and give a general reduction for single-dimensional environments to IID position auctions. As references, we've already seen the unique equilibria paper and the mechanism redesign paper. We're adding to it the sample complexity for non-truthful mechanism design, which is a joint work with Sam Taggart. Cool. Here are some main definitions for non-truthful sample complexity. We'll be looking at a stage environment that has n agents. Each agent has a value drawn from the distribution. The distributions may be non-identical across the agents, and the joint distribution, though, is a product distribution across these single agent distributions. The designer faces a feasibility constraint, meaning they have to produce feasible allocation probabilities in some space of feasible allocations. We'll be looking at a batched environment, okay, which is going to take this stage environment and look at it batched over many stages. So the idea is each of these n agents corresponds to one of n populations, and each of these m stages we're going to batch over corresponds to the Cartesian product of the stage environment. Okay, so this is imagining a setting where perhaps we're running an auction problem repeatedly with similar agents in each round, each stage, but we have the option of, rather than running independent auctions at each stage, we could bash them all together and run one mechanism to allocate all of the stuff. We could also look at an online environment where you have to allocate for each stage before seeing what happens in the next stage, but we'll focus today on the batched environment. We're going to be giving a reduction to an IID winner pays bid position auction. And just to review what that is, again, there are weights in decreasing order. There are M agents. Each agent has value drawn IID from some single distribution. In the auction, agents submit bids. They're assigned to positions in decreasing order bid, and an agent who gets position J is going to win with probability Wj, the position weight of that position. Winners pay their bids. Here are the key theorems that are going to go into non-truthful sample complexity. The first theorem is something we talked about previously in the tutorial, which is that in IID winner pays bid position auctions, the equilibrium is unique, symmetric, and efficient, meaning the highest valued agent is going to get the highest position. The second highest valued agent is going to get the second highest position in equilibrium. There is the inference result for IID position auctions, which we discussed in the last section of the tutorial. And so summarizing the bound that we are able to get from that result, if we have IID position auctions B and C, and we want to get an epsilon error in our welfare revenue estimates of auction B using a number of samples from bids in auction C, then the number of samples we need of bids in auction C is n of epsilon about m to the fourth over epsilon squared samples are going to be sufficient to get an epsilon error estimate. Cool. The main new result we're going to add to this to get a theory for non-truthful sample complexity is the following. The problem of batched, non-identical, single-dimensional mechanism design, 1 minus epsilon approximation, reduces to the IID position auction problem with batch size m of epsilon equal to n over epsilon cubed. And so the thing to think about here is that we want to convert our batched mechanism design problem with a 1 minus epsilon approximate loss into some IID position auctions, and what is the batch size necessary? How many of the stage environments do I have to batch together before I'm able to get this 1 minus epsilon approximation? Combining these three theorems, the main corollary for a non-truthful sample complexity is that there is a batch and sample complexity for non-truthful mechanism design that says we can get an epsilon additive revenue welfare loss as long as we're able to batch together m of epsilon stages, and as long as we have enough samples n of epsilon of the bid distribution in some auction C. Great. So the first two theorems were discussed in previous sections of the tutorial, so I'm only going to discuss the third theorem, which is that we can reduce the problem of getting a 1 minus epsilon approximation to the IID position auction, and we need a batch size of m of epsilon equal to n over epsilon cubed. I'm going to give you just a sketch of the construction and not the details of the proof here. The main idea of the construction is to re-envision this batched mechanism design problem. And the way it's presented, we sort of think about, okay, there are going to be these m stages. Each stage has n agents. And so you could naturally think about running a mechanism in each stage across these n agents. What we're going to do instead is think about running a mechanism for each population. So instead of grouping, again, so each of these stages has n populations corresponding to my n agents, and their m stages. So instead of grouping the stages, we're going to group the populations. Okay, and we're going to, each population is going to, the agents in each population is going to look in this grouping like it's a position auction. Okay, so we'll end up with n position auctions, one for each of the populations. And each position auction is going to have m IID agents in it for each of the m stages. Great. So here's the mechanism that's going to give this reduction. So again, so I'm going to index the populations by I, and there are n of them, and we'll index the stages by j. And the mechanism is going to be parameterized by what I call surrogate values, which are going to be for each population I, a decreasing sequence of m numbers. Great. The mechanism is going to solicit bids from all the n times m agents. We're then going to compute the rank of each agent ij amongst the other bids in population I. Okay, and so we'll let our ij be the rank of the bid of agent ij in population I. Okay, we're then going to assign to this agent a surrogate value according to their rank. Okay, and so giving each agent a surrogate value according to their rank, what we'll now do is in each stage j, we're going to optimize the surrogate welfare. So in each stage j, we're going to produce the feasible outcome xj that optimizes the surrogate welfare of the agents in that stage. Okay, where the surrogate values are exactly the surrogate values corresponding to the rank of each agent amongst their own population. Of course, this is a winner pays bid mechanism, so the winners of this batched mechanism are going to pay their bids. Okay, so I just want to observe that what we've done here in this mechanism is converted the mechanism so that the competition is not within a stage to be allocated. The competition is within a population to be allocated. And why is that the case? Well, the probability that you're allocated in your stage depends only on the surrogate value you get and the expectation over the surrogate values from the other stages. But the surrogate values from the other stages are uniformly distributed because the stages are IID. Okay, so player I in stage J sees competing players from the other populations as uniform random players from their own distributions, which get uniform random ranks. Okay, so they have uniform random surrogate values. So for every surrogate value this agent ij could have, we can compute the expected probability that this agent is served. And the higher the agent bids, the higher the agent is ranked in their population, which means the higher surrogate value the agent gets. Okay, as the surrogate value uniquely determines the probability the agent wins, this competition within each population for the higher surrogate values is exactly an IID position auction. Great. Just a quick note. What are the surrogate values you would want to use in the surrogate ranking mechanism? Well, since the mechanism only uses the order statistics of the bidders amongst their population to determine the outcome, we'd like surrogate values that correspond to the expected welfare or revenue we're generating from an agent conditioned on their order statistic in their population. Okay, so optimal surrogate values are just expected order statistics in the population. Thus, if from bid data in a previous auction we can estimate the expected order statistics, we can use those estimates of order statistics to optimize the surrogate ranking mechanism. Okay, and plugging into the theorem about IID position auctions, estimating the revenue of some position auction given bids in another position auction is based exactly on this problem of estimating order statistics. And so the previous result we talked about in the previous section gives us a method for estimating these expected order statistics. Great, that's a quick overview of the reduction from general single dimensional agent environments to IID position auctions for sample complexity.